Okay, so I'd like to talk about duality, and this is easiest to talk about for the scalar case. And so let me just do that and then just state what the extension is. So we've seen that the capacity region of the broadcast channel of y1 equals x plus z1, y2 equals x plus z2. And suppose we now add channel gains to it, because I do want to do that. Sorry, y1 equals h1, y2 equals h2. So we can write this, of course, as a vector, and this is a vector, and then we will just have h1, h2, x plus z1, z2. Okay, and let's just suppose both noise, this is zero mean and identity matrix, and let's suppose that h1 is bigger than h2. Is bigger than or equal to h2. So the channel is degraded in the sense that what we were accustomed to, namely that receiver 1 is better than receiver 2, and then we saw that the capacity region of the broadcast channel is equal to the set of rate pairs, the union over all alpha power splits of the rate pairs R1, R2, such that 0 is less than or equal to R1, 1/2 log 1 plus h1 squared p 1 minus alpha, so alpha bar. And here we have interference plus noise, right? So we have alpha p h2 squared alpha p alpha, I guess, alpha over h2 squared p alpha bar plus 1. Right? That was our capacity region. So if I draw that here, we had this rate. This is the case where alpha is, we want this thing here to be 0, so alpha is 1. Here alpha is 1, and we'll get 1/2 log 1 plus h2 squared p2. And here we have 1/2 log 1 plus h1 squared p1. And what we saw is that this thing here comes out flat and then comes in at slope 1. And so this is alpha equals 0. Right? So that was the capacity region of the broadcast channel. So what duality refers to is to try to build a relation between broadcast channels and multi-access channels. And the relation that we'd like to look at is, suppose we looked at the MAC now, and the dual MAC is the dual is considered to be the same channel, just with this channel H transposed, right? So if we called this H, the idea here now is that Y is going to be H transpose times a vector X. So it's effectively the length of this vector, these will become like X's, and now there's one Y, so we take the transpose. So rather than being 2 receivers, 1 transmitter, we have 2 transmitters and 1 receiver, and the type of channel has the same form. Here it just turns out to be scalar. right? So this here is just going to be h1, h2, or if I write it out formally, it's just going to be h1, x1 plus h2, x2 plus z, right? So that's the dual. So if we have this broadcast channel, this is considered to be the dual MAC. So we take the same channel and just take the transpose. And here we're considering noise covariance matrices with identity covariance matrix. And we'd like to find a relation between these two. And now we know what the capacity region is. So let's consider, though, in this capacity region, the natural order. So here in this degraded broadcast channel, this case, we are, it looks like we have user 2 is at a lower rate. And for the MAC, we have to turn this around and make user 1 have a lower rate. So the dual, you flip the roles. So we're going to operate at that corner point, which is, you know, if we're thinking of the MAC capacity region, we're trying to operate at this corner point. If this is R1, R2, the R1 is lower, so that we could use successive interference cancellation with the lower rate. And so let's consider the following region of corner points. You'll see why in a moment. Namely, the union, and I'll say what union we're looking at in a moment, but we're going to look at first the this one here is going to be 1/2 log. So here, this is the lower rate. This one operates with interference plus noise, right? P2 plus 1. And here we'll operate without interference. So that's that top corner point, right? So let's look at this rate. And now what we're going to do, so that one important difference between the two problems, of course, here is you have one power P, and here we have two powers, P1 and P2. So what we're going to do now is say, well, let's do the following. Let's shift, to get one power, what's the natural approach? Well, we'll consider a set of multiple access channels for which P1 plus P2 is equal to P. Okay, so this is what we'll do. So we'll consider here P1s and P2s so that P1 plus P2 is equal to P. And just study what that rate looks like. Okay, and if you look at that, you'll see right away that the rates seem to be closely, the regions seem to be closely related. And in fact, we'll show in a moment that there's a special relation, and the way I'll choose the special relation, well, I'll just choose P1 in such a way that I will get this rate. And I'm going to choose, and then I'll automatically get P2, or then I'll automatically get P2 so that I get the other rate. So what this will tell me is the following. If I choose P1, if I can choose P1 here to get this rate, or P1 and P2 to get that rate, or to put it more succinctly, if I can choose P2 here to get this rate, and I can choose, and I get the same rate here, then I have the following situation happen. That point then corresponds to a MAC with that region, right? And this slope is always 1, and remember we said the slope coming in here is 1, right? So this slope is always less than 1. Maybe I draw it a little bit more pronounced. So this is a slope of 1 coming in here. And so any MAC that I draw will always be inside like this, and we're always just getting the top corner to touch. And the claim that we're going to make is that the capacity region of the broadcast channel is the union of the capacity regions of these MACs. And that's the duality result. Okay? And the choice, and indeed that is true, and the choice that we can make is the following. I'll just write it out, what it is. You can indeed find such things. The power to be that. So we'll choose P2. Well, it's quite easy. We'll just choose P2 to give us P alpha divided by this, right? P alpha divided by alpha bar P H2 squared plus 1. And then if we, P1 is just P minus P2, if you plug that in, you'll just see that this thing here just becomes exactly this rate here. And that's it, right? So the duality result can be stated then as follows. The duality result can be stated as follows. At least for scalar channels, and then I'll say a word about that this generalizes to vector channels, and that's the one interesting observation. So the claim is that the broadcast channel P, the capacity region, is the union over all P1 plus P2 equals P of the capacity region of the MAC, P1 comma P2. Okay, that's the duality claim. That's just the same as what I just drew here. Okay, so you just take the union of all MAC regions, gives you. Now there's the reason this is interesting is because isn't so much here, but the reason this is interesting comes more once we look at vector channels, because it turns out that if we look at a vector broadcast channel, so let's go back to the vector channels. So here's our vector MAC. So we can consider the capacity region of this vector MAC. And okay, so we can write this. Let me write it first the way I wrote it before. So H1, H2, X1, X2 plus Z. And let's just call this matrix H. We can call this X. And this is Y, so we get the equation Y equals HX plus Z. Now the dual, and this thing here has a capacity region C MAC P1, P2, and let me just write it as H. Okay. The broadcast channel, let's consider the dual broadcast channel to this is that we have Y1, Y2 is equal to Y1 is H1, H2, transpose X plus Z1, Z2. And we can write this, of course, here now as Y. And this here is transpose, H transpose, right? X plus Z. And the claim is that just what we just observed here for the capacity region, if we write out this capacity region of the broadcast channel, I can write it as P and H transpose, right? And it turns out that what we just showed here for the scalar case turns out to also be valid for the vector case. Namely, that's the union over all C max P1, P2, comma H. Okay, that is the duality result. So just if I draw it once quickly, and the duality is even a little bit stronger than that. I mean, of course, there's certain orderings of decoding that are happening and so on. So if we draw our vector capacity region, remember we talked about how one type of ordering gives us rates that look like this, and the other type of ordering gives us rates that look like this, and then we timeshare. You have similar things. That's the kind of region you have. Then for the max that we get, well, here it's, I guess, not quite as obvious, like, because all the MAC capacity regions have this funny form too. But what's going to happen is that you're going to get points that always come inside. I don't think they can touch, well, they might even touch this. I'm not even sure how it exactly works now, whether it's the time sharing, it touches the time sharing line or not, but I guess I doubt it. So it'll look like something like this, something like this, something like this. It's for one of the orderings, and then you also have to do the successive interference cancellation. Like you have to do, you can view it in two ways. The max will also come and have that particular shape too. So of course they have to, they do have to touch. I apologize. So there has to be some max that's probably no longer visible. So here we have a flat piece. So some of the MACs might have like a curve that looks as follows. They might be flat for part of the region, right? And they might actually meet that curve and so on. But the important thing is that this union result turns out to be the same. Now, one reason why that's interesting is because it turns out that to find the optimal covariance, here we have optimal covariance matrices we have to find, right? So here we had this QX1 and QX2 that we were looking for. This here corresponded to this length. The dimension of QX1 corresponded to this H1 H1. This length here, right? So I have to be careful how I say this now. If this one here was n, this here is n times m1 plus m2, right? So this matrix here will have to be m1 plus m2 times n, right? Usually you want n to be, here you'd like n to be approximately or bigger than m1 plus n2, and the same thing is true here. You'd like n to be at least as big as m1 plus s2 to get the maximal amount of degrees of freedom, so that you could like invert the channel and get the full degrees of freedom going through. So what that will mean is that the length of this vector corresponds then to the lengths of both of these vectors, right? In any case, to find the optimal covariance matrices for these MACs turns out to be a convex problem, whereas it is not a convex problem for the broadcast channel. So what you do is you solve this problem for the MACs many times using convex routines, and then we can get the capacity region through this union procedure. Okay, so usually you could do the computations for the MAC, not for the broadcast channel, because you have convex programs that you can run to find the optimal covariance matrices. So that's one of the main motivations for this type of duality. Okay, so that's just a very broad sketch of duality. Okay, is this thing here. Okay? Now there's a second kind of duality, which is used a little bit less, but is still interesting. It's the dual of this duality. And that is, it turns out, oops, I didn't want that yellow, but okay, fine. It turns out if we look at the MACs, there's a duality in terms of intersections of capacity regions of broadcast channels. So it turns out that the MAC region is an intersection. So if we take this point here, remember this point here corresponded to some point of some broadcast channel, we said? Remember? That's what we just said. Well, in fact, it's a corner point of many kinds of broadcast channel, maybe one that looks like this, maybe one that looks like this, and so on, right? And it turns out that the MAC region is actually the intersection of the capacity regions of many broadcast channels. So I can quickly write it out formally for you, and then at least you'll get a feel for what this looks like. So it turns out that the capacity region of a broadcast channel where, or I guess maybe I'll, sorry, the MAC. I want to start with the MAC. Capacity region of a MAC with powers P1, P2, and where the channels are H1 and H2, the subchannels, is equal to the intersection over all parameters beta 1 greater than 0 and beta 2 greater than 0 of the capacity regions of a broadcast channel with powers P1 by beta 1 plus P2 by beta 2, root of beta 1, H1, root of beta 2, H2. Okay, so it's a strange kind of duality, but still, it turns out to be valid. But basically, you're just looking at the two corner points of the MAC region, and you're going over all possible broadcast channels, and the power, as you see here, when beta gets close to 0, the power of the broadcast channels blows up, right? So sometimes you're getting curves that are coming down you know, maybe coming down in some strange way, or sorry, it blows up in this direction, right? So it's going to be start getting really flat coming out here. Remember I said the slope was 0? So as beta, one of these betas goes to 0, you effectively get just this flat portion coming down here. Okay, and if you take the intersection of all those regions, then you will get this region here. Well, anyway, it's kind of hard to you know, somehow we'll have to also get these flat portions here too, in some sense. And I guess that will come when the two powers are identical, right? When the two powers are identical, right? Actually, we can quickly do that as an example. Why not? Suppose that y equals x plus c1, 1, and y2 is x plus c2. We should have done that as an example, actually. Suppose both noise variances are the same. Then what's the region going to look like? Then we're going to get R1 equals 1/2 log. Of course, we're degraded both ways, right? So we're just going to get the two corner points, right? We're just going to get alpha p, and R2 equals 1/2 log 1 plus alpha bar p over alpha p plus 1, right? So we're just going to get the one corner point. Because I want to get a triangle, that's what I'm trying to get at. So here we're going to get 1/2 log of 1 plus p. And I just want to see what this looks like now. 1/2 log of 1 plus p. One of the rates, so if we set alpha equals to 1, we're of course operating here. When we set alpha equals to 0, we are operating here. And here, now it bothers me a little bit. So what happens when alpha is 1/2? That's what I'm asking. Is it just a straight line? Well, if I take the sum of those two, yes, I just get the constant sum rate, right? So I must just be getting exactly this, right? Because if I take the sum of these two, I mean, you don't see it exactly, but if I take the sum, you'll see it, right? Because here I'll get 1 plus p, and then they cancel, so I'm just going on the line. So I just get a triangle. And of course, that's the one that will give me, you know, in that intersection, in this intersection will give me that flat piece. It's the one where we get the same rate, right? So that's what I wanted to get at. Because of course I can't, you know, if I take the intersection, I can't have anything coming inside, right? They all have to be on top. So that's what I wanted to look at. I should have done that as an example, right? You always get a, just, cause you don't see it immediately if you just look at it, but of course if you take the sum, then you'll see it. Yeah, okay, well. Is it clear? Maybe something too simple. Any other questions about multiple access channels? So I got a little bit of a complaint. You wanted diversity. You wanted something on diversity. I'm not sure what I should say about diversity now. So diversity is has to do with a different kind of channel model, right? So we can have, usually when you talk about this, we have channel models with memory now. So if, usually when you talk about these problems, you have, right, y, you have a y, then you have a plus equals, so you have yi and the channel h changes slowly, plus zi. So if we look at this model just for a moment, this is the model we have anyway, but suppose this is now a random variable, right? And then we're making the block length long, and so we're looking at, we're kind of looking at a problem with a compound case, right? So we're looking at a compound channel where we have, let me do the MAC. Let's do the MAC. But anyway, this was already simpler plus H2 X2i, right? So now we have a compound, we have many such MACs, one for every realization of the two fading variables. So the capacity, especially with Rayleigh fading, is going to be 0, right? Because we can never communicate reliably in a guaranteed fashion. So that it becomes uninteresting to study capacity for such models. So instead we take a little bit of a finer perspective. We don't just compute mutual informations, we compute the statistics of the mutual informations, right? Because now the mutual information will take on variable values. And then we ask questions such as, so we're getting a compound case. Some MAC looks like this, some MAC looks like this, some MAC region looks like this, some looks like this, right? And you just get a whole variation of those. And you might ask the question, when does this MAC lie inside, let's say, this region? We need the MAC, we need the MAC entire region to lie inside, or some selected points to lie inside, and we can compute the probability that it lies inside, right? And looking at that sort of types of problem, if you're inside, you say, I have an outage, right? So I can't decode because I'm communicating at a higher rate. Of course, the region itself will depend on what kind of rates you want to achieve. So here I'm just saying, if the MAC, I want to achieve rates at least on this boundary, for example, any points inside, and then of course if the MAC dominant face starts lying inside, then I can't do that anymore. Of course, if it crosses, then I might be able to, for some rates, get good performance, and for others not. So you can look at problems like this, and this relation between error probability and the or outage probability, pre-outage, and the rates is referred to as diversity. Diversity usually refers to this, and multiplexing refers to usually the rates, although with very specialized definitions that are usually used. So I commented on this sort of thing as I say, well, to me this kind of model is actually an intermediate step to what you actually want to accomplish. So let me explain that. A lot of people, I've been in talks where people have claimed that, real systems you should look at outage probability, not, average ergodic rates. But I disagree, because in the end, you're never happy if you download an email and, many of the characters are wrong, right? You would be very unhappy about this. Instead, what you are happy with is maybe you wait another 2 seconds and then the errors are corrected, right? And so that's how most wireless systems operate, unless you're talking about video coding. That's a little different because there you're taking in distortions, but you're not going to rely on these kinds of statistics to do the video coding either. But anyway, suppose we look at usual messages. So if you have an outage, what do we do in a wireless system? We have a feedback loop where the mobile station will, or in this case, the base station will tell the mobile station, say, hey, send again, or even better than sending again is to use hybrid ARQ. So send again, but encode using a different combination of, linear combinations of in your code. And you repeat that until you get it right, right? And what is that? Well, that's an ergodic rate again of a channel that's fading, but that we use many times. So the feedback lets you effectively code across multiple blocks, which is again an ergodic rate. So ultimately, so that's why I say I view this outage probability as an intermediate stage. Overall, we're interested in ergodic rates again through the feedback mechanism. Okay, that's why even for wireless cases with block fading, I still prefer to focus on outage rates, because ultimately that's what you're interested in the end-to-end perspective. So to me, outage analysis is interesting, but it's an intermediate issue. Unless you really are happy with outage, but I don't think most people are, in most practical scenarios. So anyway, in the early 2000s, from 2000 to 2010, almost every academic in the world was studying outage probability. I mean, for relaying channels, relaying was a really popular topic, but those papers that got by far the highest citations were on outage rates, right? But all that, to me, it was an intermediate analysis. It was interesting, but it was an intermediate step. And most of that analysis has now disappeared, right? Or most people don't look at that. I don't think there's nearly as many papers again today on that topic. It's an important topic, but it's an intermediate step to me. So anyway, that's my spiel. And we could, I mean, the outage rates are interesting to look at for sure. Then they give you a lot of insight, no doubt about that. Look at interference channels. So that's going to be our next topic. So we progressively are moving to more complicated channel models. So the interference channel basically includes both, to some extent, both MACs and broadcast channels. So if one really wanted to understand interference channels in their full generality, you would have to really understand broadcast channels too. Now MACs we have a full theory for, at least from a ergodic capacity or capacity perspective. Interference channels. So let me show you, and then I'll make those comments again. So interference channel, we have two transmitters with two messages. An encoder 1 and encoder 2, and they're trying to communicate to two receivers through a channel where the signals interfere with each other. And they interfere with each other. We again have memoryless models. And what's special about this, receiver 1 needs to only decode, well, it's the message 1, and receiver 2 needs to decode only the message of receiver 2, and the problem here is to find the set of rate pairs. So find the set, this is NR1 bits, NR1 bits, and R2 bits. Find the set of R1, R2 that we can communicate reliably, at which we can communicate reliably. So I'll just use that as a shorthand. Reliably. And the capacity region of the interference channel is closure of this set. This set. Okay, so that's the problem we have. As for the multiple access channel with two receivers, we'll have some kind of rate region that we want to characterize, and we'd like to characterize the boundary of this region. Okay, so let's just talk about this a little bit, this model. So where does this model appear? Well, okay, so for any place, I mean, this could be a base station sending to one receiver, this could be another base station sending to another receiver. Maybe, the cellular situation is that the base station 1 is here, base station 2 is here, and the receiver's, halfway in between. You're only connected to this. This guy has a message to send, there's another user, this guy wants to send a message too, right? And they're close to each other, and so then there might be interference that's relatively strong, affecting both, right? And, okay, so that's what it is. Now, if we have, most of these models that we're getting, since we again have two transmitters transmitting, we have the same issues as for the multiple access channel, namely timing, right? So these models again assume a common timing. So since there is a common timing, and usually you have this available, right? I mean, GPS is available nowadays. You can get very accurate timing, even down to, quite fine time levels. If you have a common timing, well, we can use TDMA to send, right? So, we could easily transmit here. Well, suppose we transmit half the time to here, we'll get 1/4 log of 1 plus p 1, let's say, by n1. And here we'll also get to 1/4 log 1 plus p2 by n2, and maybe we're even allowed to double the power because we're only sending half the time, 2. But that 1/4 really kills us, right? I mean, half, sorry. No, 1/4, right? Because I'm wasting half the time, right? So that 1/4 is really bad, right? I should be, what am I doing? I'm being silly, right? So I'm going to the point in between, something in between. I should have said this is a half. I'm only sending to one user at a time, P1 and a half. So this is the rate, this here. And then of course I can time share, right? So then I can time share between the two. Sorry about that silliness. Not sure, I was already thinking of going too far ahead. Okay, so that is definitely achievable, this point. Of course, we could now try to do what we talked about for the broadcast, for the other channels. After all, with TDM, FDM, we can actually increase the rates, right? Because if I'm sending half the time, I can actually have a higher rate. So actually, TDM, FDM should give us higher rates, just like for the MAC. It's sort of a similar kind of perspective. And we're interested, though, in characterizing that boundary. Now, I said there's both a broadcasting and a MAC component here. Now, there is no MAC component in the sense that this guy is only interested in W1 hat, but one strategy could be that we decode both messages here, right? And then we would have a MAC to here, and another strategy could be we also decode both messages here, and then we have a compound MAC. One MAC to here and one MAC to here. So we'll be talking about these different strategies in a moment. Before we do so, I'd like to do a little bit more information. Oh, and by the way, we could broadcast too, right? You could think of broadcasting, right, and broadcasting. So there's all sorts of perspectives one can take on this. A few comments, though, first, before we get into the strategies in more detail. This problem is, generally still quite open. There's two perspectives on that, this problem. One is that the problem is still very open. Namely, we have hardly any exact answers. The other perspective is there was good progress on certain classes of these models, especially Gaussian interference channels, where it turned out that the bounds that we have are within 1 bit of the optimal rate for all ranges of rates. There were some improvements on the bounds to make that work also at extremely high SNRs. But that was, it's a useful perspective to have. Still, for intermediate signal-to-noise ratios like 10 dB SNR, the bounds are still pretty far apart because 1 bit is there a factor of, might be 30–40% differences. And in any case, we really don't understand very well yet, even for scalar Gaussian channels, what the best coding methods are, except in sort of extreme cases. So that's what I'd like to show you, is what is known, what the bounds look like, how far away we are. Right. Okay. So the first thing I'd like to talk about is more information theoretic questions. Some properties, and one property is that just like for the broadcast channel, the capacity region depends only on the marginals again, and you can prove that in the same way. So the capacity region depends only on Py1 given x1, x2, and Py2 given x1, x2. Okay, so that's a useful property to get certain bounds. Now, we use that property for the broadcast channel to define a degraded broadcast channel, and then look at a channel that was physically degraded. So one could think of doing something similar here to try to solve certain subclasses of problems. This property has been used mainly to improve outer bounds on the capacity region for this problem, which is the same thing what we did for broadcast channels, right? We used this property to improve outer bounds, not so much to improve achievable rates, but to improve outer bound. Secondly, let's talk about a capacity outer bound. And we've talked quite a few times about cut sets. And so what I'd like to develop next is the simplest kind of outer bound, sort of the standard one you have for almost all problems. And here it sort of takes on an interesting flavor, this bound, which gives us some insight. So here we have our nodes 1, 2, receivers 1, 2, right? And we can think of doing something like cuts. You know, like we have a network with cuts. Well, how many cuts are there here? Well, here's one cut, right? Now this cut, what kind of rate bound will we get here? Let me just write it out for you. And it's not too hard to prove these rate cuts, but what we see here in this cut, well, there's a message W1 in this set, and in this set we have the sink, right? Whereas here we have W2 and the sink are in the same subset. So the only bound I'll get is a bound on rate 1 flowing out of here, and it turns out that the one rate bound is that the rate is less than Ix1. You can show of the receivers you have on the other side given the transmitter, what the other side knows. So the other side knows what X2 was, and there's 2 channel outputs, Y1, Y2. Okay, so for any coding scheme that achieves reliable communications, you're going to have that the rate satisfies this constraint where these random variables are actually the time averages of the statistics of the coding. So I could make that a little bit more precise, but this will give us an upper bound on the rates. I'll write it out a little bit more precisely in a moment. So that's cut 1. Of course, we'll always have the symmetric cut, right? So we'll get R2. So we always get the symmetric versions here, right? Now, there's also this cut, right? This cut has only this on this side, so it's again a rate for R1. Now, for this cut, we have 2 transmitting signals on the left side, and we have 1 on the other side, just Y1 here. So Y2 doesn't appear. So we can, of course, write that this is less than the minimum, these 2. Right? Now, are there any other cuts? Well, of course, there's this one, right? And that one has both messages on this side and both sinks on this side. So we'll just get Ix1, X2, Y1, Y2. Are there any other cuts? And here you're tempted to say no, but the answer is yes, there are 2 more cuts. And the cuts are the ones where we put these 2 nodes in one set and put these 2 nodes in one set, right? Let me just do the first circle. So these are in one set and all the others are in the other set. So what kind of bounds do we get there? Well, here again, if this is the one set, here I have R2 being transmitted, so I'm going to get a bound on R2 less than or equal to the mutual information about what's being transmitted on this side, which is X2, and what is received on the other side, which is Y2, given what the other side knows, which is X1. And then, of course, looking at it from the other way, we get the other symmetric cut. So we get these bounds here, and those are the cuts that we have to worry about. This one's easy to forget, or miss. This one's easy to miss. Okay, and now, those are all the cuts that are possible in this network. So we get 1, 2, 3, 4, 5, 6, 7 interesting cuts in this problem. Now, if we look at these, we'll see some of them are redundant. For example, this one here is bigger than this, right? This number here is bigger than that. And similarly, this is bigger than that, right? Because I can pull the x2 up front, right? So this one is redundant, and by symmetry, this one is redundant. So that's good. We got rid of 4 bounds. So we wind up with these 3 bounds. So the cut set bound for this problem looks as follows. And again, it's not too hard to prove in all of these bounds. There's a general version of this, which if I have the time, I will still develop it in the last hour. So if the capacity region then, the cut set bound says this, the capacity region is the union over all joint input distributions x1, x2 of these rate pairs, okay? So CMAC, CIC has to be a subset of this. So that's the simplest bound there is. Now we can do it actually a little bit better than this. So is that clear? I didn't prove it, but it turns out you can just do these cuts, write out these rate expressions, and then optimize over all joint distributions. Okay? Now, there's an immediate improvement we can do on this bound. Namely, if you look at these two here, well, the two messages are independent, and they can only be related through their timing. So in fact, when I do the cut set bound, I could have done it a little bit more carefully and built in a time-sharing random variable, and then add this condition to it, where t is, I think in this chapter I'm using q for some strange reason as time-sharing random variable, and then I can add the time-sharing everywhere, which I should have done, and then I get a better bound. So this gives me a better bound because now the x1s, x2s cannot have any joint distribution. They're limited by, to be conditionally independent given the timing. So here the q represents the time. Okay, so this is a strengthening, an obvious strengthening of the cut set bound for this problem. Is that clear? And the way you get this is just by making sure you don't drop that q random variable when you write out the, like we've always done over and over again. And sometimes we've dropped it if we didn't need it, but sometimes we've kept it to make sure we keep the time sharing, like for the MAC. So this is a simplest outer bound. Okay. Now let's go to Gaussian interference channels. So we may as well right away jump to that. Not integrated circuits, but interference channels. Okay, so what I'm going to do is we'll start with the following simple interference channel. I'll draw it with a graph. It's a little bit easier. Effectively, what I'd like to write here is the gains we have on the channels. So let's say C11, C22. This will, let me give this a name x1 tilde, so I'm just changing the variables. You'll see in a moment why I'm doing this, because I want to change this channel to be something else. So I'll call it the tildes, and this I call C12. This is going to be C21. Okay, so here, the idea here is that this one here is C11 x1 plus C12 x2 plus Z1, and this here is C21 x1 plus C22 x2 plus Z2. And we want this thing here, so we're looking at the most general case. This is zero mean variance N1. This is zero mean and variance N2. Okay, so I think you agree with me this is the most general kind of Gaussian interference channel with all possible types of interference values as well as noise variances. And of course we have power constraints as usual. You know, here we'll have P1 tilde as our power constraint and P2 tilde. So why am I writing all these tildes? Well, the reason is I'd like to convert this channel into something called a standard form. And so let's do that, for which we don't change the capacity region, but for which we get a simpler form. So I'd like to get rid of all these parameters. I'd like to get to the smallest number of parameters I can live with so that we can focus on those problems. And this is usually what everyone does as a first step. So the first step to do is just the following. I'd like to make the noises to have unit variance. Okay, and that's easy to do, right? I just take y1 and divide it by the root of n1. And that doesn't change any mutual informations, right? Because if I divide by a root of n1, I can always multiply by it again, right? So I'm not losing any information by doing that. So our object here is to convert to something called the standard form. And so what we do is we let y1 equals y1 tilde by root of n1. And then of course we get, well, let's just write it out, c11 by the root of n1 times x1 tilde plus c12 by the root of n1 x2 tilde plus z2. So this is what I'm going to call my z1, sorry, plus z1 without a tilde. This will be zero mean unit variance, and we'll do the same thing to y2. And this won't change the capacity region, obviously, of this channel. Root of n2, x1 tilde plus c22 by the root of n2, x2 tilde plus z2, which also is zero mean unit variance. Okay, now the next step I'd like to do is I'd like to have gains of 1 on the main links. How do I do that? Well, all I need to do is, if I'm sending it power here p1 tilde, then by changing the power constraint to be p1 tilde times c11 squared to n1, I can consider this to be a gain of 1 with the power, because it's just like boosting up the signal in power, and I can do the same thing here. And by doing that, I'll get gain of 1 here and a gain of 1 here, but I'll have to change these gains because I, of course, will have to multiply this by the opposite to undo that power gain I've given here. And that will give me the channel in standard form. So that's what I wanted to accomplish. So I wanted to make, the goal here was to make the noise variances be 1, step 1, and then to make the direct gains to be 1, step 2. And the capacity region of these transform channels are the same as the original channel. Okay, so now we set the following. Now set. So I just have to define the new parameters. P1 to be equal to C11 squared by N1 P1 tilde as the new power constraint. P2 equals C22 squared by N2 P2 tilde. And then I want to define crosstalk parameters. A12 will be equal to C12 squared C22 squared N2 over N1, and A21 will equal to, so that gives me the C12 over N1. And then I have to undo the fact that here I multiplied this power, I boosted this power, so I have to reduce it again. Right, and the same thing here, C21 squared by C11 squared N1 by N2. And then I get a new channel that looks like this. Y1 equals X1 plus the square root of A12 X2 plus Z1, and Y2 equals square root of A21 X2 X1 plus X2 plus Z2. Okay, and you'll notice the gains I've made. The gains I've made are now positive too, right? Because I've put the squares in. So, but that isn't that. Well, you could argue whether that's a big deal or not. But I mean, here everything is rotationally symmetric, plus minus 1 anyway. So Still, you might want to keep the sign in one of these that the negative is here and may think, well, does that play a role or not? It's actually an interesting question. I don't think so, not for the Gaussian channel, but if you have limitations to modulation constraints and stuff like that, then you might want to worry about stuff like that. But in any case, we could do that too by just keeping the sign on here. So I could just multiply here by the sign, and then I would just have the sign corresponding to here. But in any case, I want to study this particular channel model. All right? So I guess I could... anyway, so this is the way I've done it. I could think of just taking the square root of this and then keeping the sign. And then definitely the capacities will be the same. But this is the model that I'd like to look at. So we're going to look at this model here. Right, so it's going to be 1. But the important things are the gains of 1 and unit variance. That's what I want it to get at. This here is A21. We're anyway going to often study the A's are going to be the same for most of the examples we'll look at. Okay, so is it clear why I do this? I just want to get rid of parameters, and be able to study a simpler version of the models. We've reduced the number of parameters now here from 6, 1, 2, 3, 4, 5, 6, to just 2. Right, that's the nice thing. And if I had kept the sign, I could definitely claim the capacities are the same. I have to think about the justification for getting rid of the sign, to be honest. So I have to think about that. I don't think it does play a role, but I'm now not 100% sure. Okay, so let's study this model here from now on. So we simplified the form of this channel by collecting these parameters together. We can now study that outer bound, which I erased for the Gaussian channel. So I think it's useful to at least walk through this. So remember, we had R1 less than or equal to I of x1y given x2q. And just like for the MAC, right, where we had the q, we're going to here get that this cut-set bound, the Gaussian Gaussian distributions will always be optimal, and you already see that all the steps are the same, right? Y given x2, q equals q, minus 1/2 log 2 pi e times 1, because h of y given x1, x2 is just the entropy of the noise. And so this whole thing we can show as less than 1/2 log of 1 plus p1. Right, because here I can subtract off the x2, and I'm left with a clean channel, right? So, and that's clear that that should be an upper bound. So this is the outer bound, cut-set bound. Right, that's the cut-set bound. But we'll get the same bound for R2. So the one that's going to be interesting is going to be the last bound. So let's write that here. This is one bound, 1/2 log. And this should make sense because this is clearly the best rate we can achieve if we're sending information always to user 1. And then the other cut-set bound will be this, for the same reason. But now the last one's going to be interesting because it involves a vector problem. Remember, this one here was I of x1, x2, y1, y2, right? Given q. And here one can show that this is, this is h of y1, y2 given q minus 1/2 log 2 pi e squared, because it's a two-dimensional, right? It's h of y1, y2 given x1, x2, which is h of z1, z2. So that's just going to be the determinant of the identity matrix, but we'll just get that squared, which makes sense, I hope, because after all, we have a Gaussian vector with independent entries of length 2, so this 2 will just come out front, so we'll just get log of 2 pi e. Now this thing here is again going to be upper bounded by a Gaussian, but notice that it's a a vector. So we have to say, well, that's less than 1/2 log of 2 pi e squared times, and since the 2 pi e squareds cancel, we'll just get rid of these. So this is just going to be the determinant of the covariance matrix of y1, y2. Okay, I got rid of the q due to concavity. You can get rid of it. Anyway, you'll get this. Okay, so those are the 3 bounds of the cut set bound. Looks like this. 1/2 log det q y1, y2. Okay, so we could compute now what q y1, y2 is. Let's do that maybe. Well, that's going to be the determinant. And what's the covariance matrix here? Well, we'll need the variance of y1. What is that? Well, it'll be p1 plus a12 p2 plus 1 p1a21 plus p2 plus 1, and then we need the cross correlations, which are going to be square root of a12 21 this one p1 plus square root of a12 p2, and similarly here, right? And now we have to take the determinant of that, which I don't really want to do. It's a little bit ugly, but it's not hard. I mean, it's not hard. I just don't want to write it all out. Okay, so that's what comes in here. All right. So the capacity region of the interference channel is a subset of the union over all x1 well, it's a subset of this. 0 less than or equal to, because we've already done that union. Okay, that's one thing. And one small improvement we can do on this, in fact, there is an improvement we can make, and that uses the fact that the capacity region depends only on the marginals. Okay, what does that mean? That means we can make the noises have any correlation we want, right? The margin, even if the 2 noise terms are completely correlated, suppose these 2 are the same noise random variables, then the marginals don't change. And we said the capacitor region doesn't depend on the marginals, so in fact we can optimize this so that when we do the cross correlation coefficient, we will get an extra term appearing here, plus the rho that appears here, right? Plus rho, and that might be useful to get a better bound. So in fact, we can improve the cut set bound by adding here a minimization over all rho. So now this q is a function of rho, and we'll have r1 plus r2 less than or equal to rho. And now we should check whether we get something different here too, which we might, because after all, this noise variable, we had that x2 in the conditioning. Do we get anything? Let's check quickly. X.
Sorry, I missed the last part. The rho part, can you just...
Oh, well, the capacity region depends only on the marginals, right? So let's study then a model where these 2 are correlated.
Okay.
That's it. This is, I'm just computing the cut set bound for that new model. For this case, what's going to happen in this covariance matrix, I'll get a rho appearing. And so, yeah, and now I can still choose any rho I want to get my upper bound. But I'm just making sure that that rho doesn't appear anywhere else now, namely in these 2 bounds.
Right.
So we can check that quickly. Here we have I of x1, y1 given x2, and you see y2 doesn't appear, so it doesn't appear there. Right. So in fact, this is a new bound where we can here minimize over rho. That is an improved bound. Okay, so this is how, like, using this fact the capacity depends only on the marginals comes in as useful, right? And in fact, for the broadcast channel, we could have done the same kind of thing, because there we could have correlated the noise. In any outer bound we do, we can correlate the noise. And this is in the broadcast channel. I didn't cover that here. That's called Sato's upper bound. So there's a simple observation, but sometimes that Sato upper bound even gives you capacity, and that's how the three groups, so there were three groups that first found the sum rate capacity of the vector Gaussian MAC with dedicated messages. They just took Sato's bound and showed that the dirty paper coding achieved a sum rate that corresponded to Sato's bound. So that was the converse that you need. Now for the interference channel, we can do the same thing because the capacity region depends only on the marginals. That's what we're doing here. Okay, so this is an improved upper bound. Sometimes useful. And of course this rho, well actually I don't know now what parameters that rho takes on. It might be able to go between minus, negative could sometimes be useful, I suppose. I'm not even sure. Actually, well, I'm not sure. And this is again where I'm not sure whether we shouldn't keep the signs in here. You know, maybe I should have kept, like if the original term was negative, maybe I should have kept the negative. I'm not even 100% sure. I have to think about that. It would be nice to have an example where you can, where you do want to keep the signs here rather than just the positive values. I should check that actually. I know there were some papers that did certain strategies for that, but I don't remember if they were fundamental or not. So it's something I have to think about. Okay, but this is just using the marginals. Okay, so you get a better sum rate bound. Okay, right, so that's converses. So, you know, again, converses aren't as nice as coding strategies, so let's go to the coding strategies. Being constructive is always more fun than being non-constructive. But, you know, both are important, and, you know, usually, since so little progress has been made on improving achievable rates, most people have focused on their research on converses, but it's always tough, it's tricky to find good new converses, but it seems to be even harder to find new constructive methods, right? Nobody is even trying anymore, I almost find. I don't know if that's... Meanwhile, new constructive methods are much more rewarding, right? I mean, that you can patent. You can't patent a converse. Or you know, at least you're building something, constructing something new. Anyway, so let's just talk about coding methods, coding strategies for this channel. I've already talked about some of them. So the most basic coding strategy is, what do we usually do with interference? We just treat it as noise, right? We say, we have to live with it, right? So the first method, the most basic method, is called to treat interference as noise. That's become so popular, even in the theory, that it's even gotten its own acronym, TIM. That acronym only appeared like 8 years ago. Nobody ever bothered to give something so stupid an acronym before, but now it's there. TIN. Anyway, it's not as stupid as I made it sound. It's actually sometimes the best thing to do, as I'll describe, which came as a big surprise. So it turned out there was about 10 years ago, there was the first new capacity result for interference channels since like the 70s was discovered, and it involves showing that treating interference as noise is amazingly sometimes optimal, which is remarkable because the interference isn't noise. It's actually a code word, so I think that it surprised me anyway. Okay, so the first rate, we treat interference as noise. What do the rates look like? Well, it's just R1 is equal, you know, is I x y1, right? Right. And if okay, so 0 less than. Right. So if whenever that might, I don't know if x1 y1 x2 y2, and then we take the union over all. I guess we want to do this for the Gaussian case, so let's do it right away for the Gaussian case. We'll just write out what these equations are. Equals interference to signal plus noise ratio, right? 1 plus P1. What's the interference? Well, it's the cross term. Now I erased it. This here is root of A21. This is the root of A12. So the interference is coming from here, so it's going to be A12 P2 plus 1. So interference plus noise ratio is 1/2 log of 1 plus P2 over A21 P2 plus P1. Okay, now that being said, and now of course I want to, Now that being said, to be honest, I cheated here. In this following sense, I chose my signaling to be Gaussian. Is Gaussian the best with interference? Not necessarily. Gaussian is usually the worst case noise, right? So there's no reason to believe I should have chosen these signals to be Gaussian, and there was a bunch of work showing actually you shouldn't use a Gaussian, you should actually use in general like discrete signal sets, you know, like QPSK and so on, and you can do better. So Daniela Tuninetti did quite a bit of work on that topic, and you can actually show you shouldn't use Gaussian signaling, which sort of makes sense, which makes it even more remarkable that using Gaussian turns out to be optimal for some interference channels. So it turns out that when the interference parameters here are very small, but still finite, so not going to, it's not a limiting result, it says that below a certain threshold of interference values, it turns out that you should use Gaussian signaling and you should treat interference as noise. That was the remarkable result. I mean, I think that's surprising. More generally, though, you shouldn't use Gaussian signaling. Right. So I'm just writing it like that in that sense to be useful. In fact, we shouldn't even use the maximum power. Even if we're using Gaussian signaling, we shouldn't perhaps be using the maximum power. So you could think of taking here the union over all beta 1 and beta 2. So suppose we even use Gaussian, but suppose we just sometimes don't, we say we use different power levels that are less than this. So beta 1, beta 2, beta 2, beta 1. Maybe by backing off on power, we create less interference and it's beneficial. Now it turns out you'll find that the best betas to use here are come in 3 sets. 0, 1. That one's kind of obvious, right? There's no interference. 1, 0, or 1, 1. So there's no point in ever not either sending with full. And the reason is if we look at the rates that we get here, and now is where I would have needed my computer, you'll find that the rates that you get, so here's R1, R2, so one of them is here, one of them is here. Of course, those are the maximal rates, like 1/2 log of 1 plus P1, and this is 1/2 log of 1 plus P2. If you use, so we're either operating here or we're operating here, and if we use both with full power, we might be operating here. And then by changing beta 1 and beta 2, you might be getting rates that look something like this, right? So then there's no point in using anything else than these two, because you could even now take the convex hull of those 3, right? And that would give us the treating interference as noise rates with Gaussian signaling. But of course, as I emphasized, again, Gaussian signaling may not be the right approach either. Here I'm just by default using Gaussian signaling to compute this. Okay, and in general, again, it's not necessarily optimal to use Gaussian signaling. Okay, so that's the first strategy, which again, it sounds silly, or it sounds oversimple, but remarkably, this is actually sometimes optimal. To treat interference as noise. It tends to be good when the interference is very low. Okay, now let's go to the second method. This method turns out to be good when the interference is at a medium level. And guess what? It's also not a difficult one. It's TDM-FDM. TDM-FDM. What do we do now? Well, kind of obvious. We send to user 1 a fraction tau of the time, and we send to user 2 a fraction tau bar of the time, and we use power increases to reflect the fraction of time we're getting. So we get R1 is equal to tau 1/2 log of 1 plus P1 by tau. R2 equals tau bar 1/2 log of 1 plus P by tau bar. So this is the usual way, 4G or 5G will operate with interference, right? This is pure orthogonalization. This is like using OFDM and assigning frequency and time slots jointly across a larger network. Of course, you lose frequency and time reuse you can't use now, but anyway, that's how it's usually done if you have coordinated transmissions. You assign resources, and the resources are time here or frequency, and the power, of course, power, P2. Okay, so that one's quite straightforward. And then the third strategy works really well when the interference is really strong. So why would interference be strong be interesting? Well, there could be some scenarios where it is. One example is, for instance, if this is base station 1 and this is mobile station 1, and this is base station 2 and this is mobile station 2, they've crossed into each other's zones, and then of course here the interference is strong. Okay, and the natural method to use when the interference is strong is decoding the interference. Which already sounds tough, right? Because now we have to decode two messages, but it's like it's like building a MAC. Right? So in this case, decoding interference we would get a compound multiple access channel, one to this receiver and one to this receiver. So let's think about that for a moment. Okay, so if both users decode both interference, so if both receivers decode both messages, that would be like decoding the interference. We would get a compound MAC. And so we can write out the rates of the compound MAC. The compound MAC means we'll get an intersection of the rate regions of two multiple access channels in terms of the bounds. So if I write the rate regions information theoretically, we would have R1 less than or equal to the minimum. So we have two MACs. So what we'll get is I of x1, y1 given x2. And rate 1 will also, we're decoding at the other user, I of x1, y2 given x2. And by symmetry we have this. X2, y2 given x1, I of x2, y1 given x1. And R1 plus R2 also involves a minimum of two regions, because again we have a compound MAC, so we have to consider all bounds on the sum rates for both receivers. Okay, so that's the region, just writing it out in full-blown form. So this will be another rate region that we can achieve. Rates assigning this, but one comment here which is very useful to observe. These two mutual informations correspond to, let's take a look at the first one. Remember where we got that bound from for that MAC? That corresponded to the error event that message 1 is wrong, but message 2 is right. Message 1 is wrong at receiver 2, but message 2 is right. Do we care about that error event? The answer is no, because we don't care if user 2 gets message 2 wrong, right? So we can actually throw out these two bounds. They're not necessary. Okay? It's just an interesting observation which simplifies the achievable region. Now, how you would build a decoder that accomplishes this, don't ask me, but with typical sequence decoders, you could accomplish this. So formally you can do this. Okay. It turns out that regions that you get like this, you can massage and show that there's another choice of random variables distributions for which you may as well decode both. So that's what turns out usually for problems like this. But in any case, from an information theoretic perspective, it's nice to get rid of bounds because that can enlarge the region, and it does here for specified probability distribution. So that is good. So we get these bounds here. So those are the three basic strategies: treat interference as noise, TDM, FDM, decode interference. And the treating interference as noise is good when the interference is small. TDM, FDM is good when the interference is intermediate, and this is good when the interference is strong. Okay, so that's just the first general picture of strategies, basic strategies here. So it's just some remarks on that. We can now, of course, mix all strategies, right? So adding time sharing is good. With power, sharing can help. To all of these regions, well, we already had it here. This is time sharing, can help. All regions. And B, we can mix the methods, and we'll do that when we get to the Han-Kobayashi region. Right? Remember, for the for broadcast channels, we had superposition coding and Martin coding. We stacked them on top of each other. We're going to do the same thing. So Han-Kobayashi effectively puts these things together and adds one new twist. Okay, but it effectively puts these together, with one new twist being rate splitting and partial decoding. But that's the one new twist. Oh, okay. So that's what I wanted to say. Okay, so now I would have needed my computer, but let me draw just generally what the regions look like in my head, because I don't have it in my book. So I have to try to remember what these regions all look like approximately. So what we'll look at is a plot, a plot that I'll have to try to remember from memory. So let's do rates examples. So what we're going to choose is A12 equals A21, right? So the cross interference is the same. And what we'll do, I'll just do a plot. I'll do various plots here. And they're going to be a little bit from memory, and hopefully I get them right. And let's start with here that this is low interference. So suppose these parameters are 0.1. So the interference is 10 dB down. Then if we drew the cut set bound, first of all, we'll get this pentagon. If we added that row improvement, we would shift this curve down, but let me not draw that for the moment. Now, at low interference, of course, treating interference as noise works relatively well, so we operate here and maybe at a point like this, maybe at a point like this, and then we can time share between the two. So this here is treating interference as noise. TDM, FDM is a little bit worse generally, so it might get rates that look like this. And of course, decoding interference really sucks because, I mean, it's very hard to decode anything, so you might get a region that looks like this, right? Here, this is a pentagon, right? But these two will be the same there, so this will be decoding interference, right? So that's at low crossover probabilities. Now, as we increase this, so let's go to an intermediate range, something like 0.5. So now the interference is 3 dB down. Everything starts shifting. Now the treating interference as noise gets worse, of course. So we can redraw all these curves. The cut set bound, by the way, these curves don't change, these ones here. This one here doesn't change either, right? Or no, does this one here change? What was it again? The cut set bound. This one must shift a little bit in and out, but these two curves, of course, these two lines remain the same. So now treating interference as noise might even start looking like this. It might even go below the time sharing line. Might even happen, right? Which means we may as well time share treating interference. If we allow, well, if we don't allow time sharing, it would look like this. Doing TDM, FDM, so this is tin. TDM, FDM will start looking better. In fact, it'll give us the best curves. And now decoding interference will start getting a little bit better, but still not great, right? Something like that. Okay, and now, so that's the picture. Now if we go up to parameters 1, as soon as this is 1, what we're going to see tomorrow is that actually, this is already called strong interference. It'll turn out that decoding the interference turns out to become optimal, right? So we'll get a curve that looks like this. And that means we can improve this outer bound in some way. Treating interference as noise is pretty bad. This is tin. This is decode interference. And in fact, this decoding interference for this, we'll see this tomorrow, is actually achieves capacity. And the reason it achieves capacity is we'll find an outer bound that matches it. Because it'll turn out we can decode both messages. So actually these bounds I think should even meet in that case. I think they even meet. They must somehow. Anyway, we'll talk about that. And TDM FDM is still pretty good, but it starts, it starts getting not as good anymore. So this is TDM FDM. Actually, TDM FDM is always the same curve, right? Because if we do TDM FDM, we're getting rid of the interfering term completely. So this curve always stayed at the same spot, right? It's just bang on, right? So that's also one reason why it's not bad. It doesn't depend on the interference, right? So, okay.